Okay, we are all back. So let's start the next half session. So our next speaker is Alejo Rossia, and he will tell us about Wilson is not anonymous. Okay, let's welcome.
Thanks a lot. Thanks a lot to the organizer for allowing me to give this talk today in this very exciting workshop. And this talk is based on this short note that we published last year in collaboration with Quentin Bonfoy, Luca Di Luzio, Christophe Grosjean, and Ian Paul. And very differently to many other talks this week, the only goal that I have today is to bring you some peace of mind. And you will see why. Let me start by doing some remarks on SMEFT. I guess that you all know at least the basics about the standard model effective field theory by now. But let me remark a few things. First, it has exactly the same field content and the same gauge symmetries of the standard model. And in this talk, we will work only with dimension 6 operators. That's where we will cut this expansion, this series, and we will work in the Warsaw basis. And in particular, I want to stress or to highlight these kind of operators that you see here that involve the Higgs doublet, the electroweak gauge bosons, and the quark fields. And I want to highlight them because they all modify the gauge vertices of the fermions in a chiral manner, in the sense that they can give different contributions to left and right-handed fields. It's quite clear from the expression of the different operators. And that will be important for the next part. I want to remember very clearly the word chiral, because it will be important in just a minute. But before going to the question that I want to answer, let me introduce to you the other big topic of today, of this talk, which are anomalies. And anomalies, in case you don't remember, come from this very nice idea that some classical symmetries are not respected at the quantum level. And those symmetries which are not respected at quantum level are called anomalous symmetries. Their importance depends on whether they are gauge or local symmetry, local or global symmetries. For global symmetries, the anomaly is not really a problem. It doesn't bother you so much or us. And it has the nice property that it does not renormalize. This property also applies for the gauge symmetry anomalies. And from this property, one can use it to extract some phenomenologically relevant information. But today I will not talk about global anomalies, and this is not the focus of my talk. Today the focus will be on gauge anomalies. Very generally, because there are some subtleties that I will not go into today, a gauge anomalous symmetry renders your QFT inconsistent, and for sure non-renormalizable. And therefore, when you have a gauge anomaly, you want to cancel it. So in order to know how to cancel it, you need to know how to compute an anomaly. So let me go and do a very quick review. The textbook computation is to take this green function of 3 conserved currents. These currents must be conserved at the classical level, and compute the divergence of this green function, and in particular, take the divergence of the one loop level, of the one loop contributions. At one loop level, you will see that the important part, the kind of diagrams that really matter for the anomaly, are these kind of diagrams where you have a triangle loop between the 3 currents, and you let all the fermions in your theory run inside the loop, as long as they're charged under these currents, obviously. And you will find that in general, this divergence will come proportional to a polynomial called anomaly polynomial, DEIJK, which can be computed very simply from the generators of the symmetries on the representations under which the fermions transform. And you have to take the trace of these generators, as you see here, sum it over the left-handed fermions, and then subtract the same sum but over the right-handed fermions. The diagram of the sum is the same. And from here, you can clearly see that if the left-handed and right-handed fermions have exactly the same charges, transform exactly the same under these symmetries, this will cancel, and you will have no anomaly, and therefore these symmetries will be conserved at the quantum level. But if they don't have the same charges, if you want to cancel the anomaly, you need some non-trivial cancellation here to make this zero. So now the question that we want to answer is whether higher dimensional operators that you add in SMEFT can generate a gauge anomaly in the SMEFT that in principle is not there in the standard model because of its field content. So far, until last year, I will say, most people believe that this was not the case, that a dimension 6 gauge invariant operator could not generate a new gauge anomaly, and that the absence of gauge anomalies in SMEFT was guaranteed by the field content of the standard model. But some people started computing this and checking it because there was no proper check, to be honest, in the literature. And for example, this group in Germany also did some computations. They computed, again, this same kind of triangle diagrams where in one of the vertices, they included the dimension 6 correction of that vertex induced by the operators that I showed you at the beginning. And they found that in principle, there could be some gauge anomalies. And in order to cancel those new gauge anomalies, you needed to correlate the Wilson coefficient of those dimension 6 operators in a non-trivial way that you can see here. But this was strange to many people, in particular to my group, because it's not hard to find some counterexamples. And with counterexamples, I mean some extension of the standard model where the BSM part is completely anomaly free, the standard model itself is completely anomaly free. When you match it to SMEFT, and you find that they don't respect these constraints. In particular, the simplest model that you can think of is adding to the standard model a singlet bifermion, basically a type 1 seesaw that you can use to give mass to the neutrinos. But I will not go into the details of the counterexample. Instead, I will invite you to revisit this question, starting with a toy model. Let's consider this toy model, where we have a U1A gauge symmetry and U1B gauge symmetry. We have a complex scalar which has a charge only under U1B with some potential. And we have two families of Weyl fermions, massless Weyl fermions with both chiralities, which have a vector-like charge under the U1A symmetry and a chiral charge, axial indeed, under the U1B gauge symmetry. And on top of that, we add some dimension 6 operators that reproduce exactly the same structure of the dimension 6 operators of SMEFT that we're interested in, as you can see here. So with this, you can ask, okay, I have a chiral gauge symmetry in U1B. Is there any constraint on the charges of the fermions coming from gauge anomalies? The answer is yes, there is a constraint. If you neglect for a moment the dimension 6 operators, you can compute it with the normal techniques that you learn from any QFT textbook, and you will find that the constraints on the charges are the ones that you see here. And these are the gauge anomalies in the renormalizable theory. Now, what does it happen when you include these dimension 6 operators? Let's see. So first, you observe that this dimension 6 operator effectively modify the gauge interactions, in particular where when you give a non-zero BEV to the scalar, this will modify the gauge charges of the fermions in a chiral fashion. So you can compute the same kind of triangle diagrams that were computed by Kat et al., where in one of the vertices you include this correction at order 1 over lambda square. And you can ask this current basically to be conserved at the quantum level. In this current, the second term that you see here, the last term, is what generates the gauge anomaly conditions that I showed you in the previous slide. Is the one that is generated by the dimension 4 gauge interactions. And then you have here these two pieces, which are the ones that generate these kind of vertices at order 1 over lambda square. Now you ask for this current to be conserved at quantum level. and you find some constraints on the Wilson coefficients, just like Kat et al. Did in their paper last year. And you can see here that the look of the constraints are basically the same, except for the toy model being much simpler. But now I ask you to pause for a second and think about what you learned in quantum field theory. And there, when you want to introduce a gauge symmetry, the first thing that you have to do is to start with a global symmetry and check whether that is properly a global symmetry, find its classically conserved current. And after that, you ask, can I ask this current to be conserved at quantum level in order to gauge this symmetry? If you find that there are no anomalies, you can gauge the symmetry safely without any problem, and you have a gauge theory. If you apply the same reasoning to this case, you will find, using just equations of motion, that this current is not conserved at the classical level. Therefore, what we were asking is completely nonsense. You cannot ask it to be conserved at quantum level. Therefore, you go back to your toy model and you analyze the global symmetry associated to U1B, and you think, okay, what is the classically conserved current? It turns out that the classically conserved current, it has an additional term that you can see here, which involves the charge of the scalar. Perfectly. It's quite understandable. So this was a forgotten piece in the computation that we were doing. In a diagrammatic way, this means that we forgot some diagrams when we were computing those triangle diagrams. There are some extra diagrams. Maybe they can change our result, maybe not. Let's find out. So let's compute again with the proper current in this case, including dimension 6 pieces, and let's compute again the divergence of this 3-point green function. Let's do it in the broken phase where we have this BEP for the scalar. And when you compute the diagrams with this current, you will see that first you obtain the diagrams that we were computing before, where you have the 3 currents in the vertices, and in one of the vertices you have this 1/λ² contribution. But on top of that, you have these additional diagrams, where you have a Goldstone boson, which comes from the scalar part of the current. You can see here. And then you have the Goldstone boson propagator, and then the Goldstone boson interact with the 2 fermions through the dimension 6 operator. And therefore, this diagram has the same dependence on the cutoff of your HEFT and on the Wilson coefficient that this other diagram. Even more, when you take the divergence, these 2 diagrams cancel exactly. So therefore, all this divergence of the 3-point green function does not depend on these dimension 6 Wilson coefficients. Hence, we cannot put any constraints on the Wilson coefficients from these anomalies generated by triangle diagrams. But the interesting thing is that we found a much easier way to arrive exactly at the same conclusion, and that is much easier to extend to the standard model effective field theory. This other way is basically using a bosonic HEFT. In order to use it, let's add some Yukawa terms to our toy model in order to give a mass to the fermions. We can adjust the Yukawas and the gauge couplings in such a way that the fermions are much heavier than the gauge bosons, and that will not change the anomalies because the anomalies are completely independent of Yukawa values, of precise Yukawa and gauge coupling values. So we have these fermions which are all much heavier than the bosonic degrees of freedom in our theory. We can integrate them out and get an HEFT where we have only bosons. That HEFT still has to know about the anomalies. If there is any gauge anomaly, it has to know about it. I will not go into the details of the argument, but it has to know, and it will know it, and it will acknowledge these anomalies through the Wess-Sumino terms. This is a kind of terms that are introduced in several textbooks. And in the Wilson coefficient of these Wess-Sumino terms, you will find basically the anomaly polynomials. If the dimension 6 operators enter in those Wilson coefficients of the Wess-Sumino terms, therefore they can generate a gauge anomaly. So let's see if they enter or not. We can compute these Wess-Sumino terms for our toy model, and we find the following. These are the West-Zumino terms, where you see the field strength of the U1A and the U1B gauge symmetries, and here you have the gauge fields. The terms that you find on the left are called axionic terms because they involve the gauge boson, the Goldstone boson, and they're exactly the same kind of term that you find in axion physics. And the others are called generalized Chern-Simons terms. And you can see here the Wilson coefficients, they all depend only on the gauge charges of the fermions. And they do not depend on the dimension 6 Wilson coefficients that we had in our toy model. Even if we, trust me, we computed with those Wilson coefficients, we took them into account. Therefore, we cannot put any constraint Wilson coefficients from triangle diagrams because they do not generate any gauge anomaly. Now, it's clear that this technique is very easy to extend to the standard model effective field theory because we can deform it, we can forget basically about the experiments, and we can suppose that all the fermions in SMEFT are much heavier than the gauge bosons and the Higgs indeed. Or indeed the Higgs, you can make it heavy too and integrate it out, it doesn't matter for the kind of diagrams that we compute. And you integrate out all the fermions of SMEFT, you keep only the gauge bosons, and you find these in West-Zumino terms. If you do it only with the standard model, you forget the dimension 6 operators, you will find that these West-Zumino terms in the neutral sector of the electroweak gauge boson sector look like this, where you see first the axionic term, where pi3 is the Goldstone boson that will be absorbed by the set, and then the GCS, the generalized Chern-Simons terms with the hypercharge and W3 gauge bosons. And the Wilson coefficients here depend on the hypercharges. These are the hypercharges of all the fermions. You can compute the gauge variation of this part of your bosonic EFT derived from the standard model, and you find the following. And you see here some polynomials on the hypercharges that you want to cancel in order to cancel the gauge anomalies. And those are just the usual gauge anomaly cancellation conditions that you find in the standard model and that determine the hypercharges of the fermions. Therefore, our technique already reproduces the well-known results. Excellent. So now let's consider the dimension 6 operators that I was talking about before. So you compute exactly the same kind of diagram. Now in one of the vertices, you consider the dimension 6 contribution of these operators. At the end, you find out some West-Zumino terms which look like this. This is a fancy way to write them because we have redefined the fields with this combination A0, which is this particular combination of B and W3, which is basically what will be the setup to some terms, up to some G and G prime, and its field strength. And these coefficients, C and E, depend on the dimension 6 Wilson coefficients of the SMEFT operators in general. Then you can start playing with these terms, and you will see that they all cancel, basically. Up to some integral by parts, they all cancel, and then the gauge variation of this part of the EFT is 0. But this is quite obscure, I know it. So let me show you in a bit of detail part of the computation. Let's pick all the terms that can give you the term pi3 BB tilde. First, we have this term where F0 contains B, nu. So from here you will have a pi3 B tilde. And then you have this term where you have inside A0, you have the partial derivative of pi3. So this will give you this kind of term. Now, this term on the right, you can integrate it by parts, and you get exactly the same operator that you have in here. And therefore, the only thing that it's left to do is to see what is this equal to, this combination. You can compute this C and E with techniques that are explained in our paper, and just triangle diagrams, basically. And they depend on the dimension 6 Wilson coefficients in the following way, where you see here C phi D, C phi E, C phi L1, C phi L3, C phi Q1, all the dimension 6 operators that apparently generated these spurious gauge anomalies. And now, using this relation between the hypercharges of the Higgs boson, phi is the Higgs boson, and the fermions, which is enforced only by classical gauge invariance of the Yukawa terms, you see that, for example, this piece and this piece will cancel. And the same happens for all the other pieces. And therefore, this is equal to 0. You can do exactly the same for all the other coefficients that you get. At the end, all the dimension 6 contributions cancel out, and therefore you cannot put any constraints on Wilson coefficients at dimension 6 from gauge anomalies generated from triangle diagrams. That's the conclusion, and that leads me basically to a few final words. This is just a repetition of what I just said. Dimension 6 carrier operators do not generate gauge anomalies from triangle diagrams. SMEFT at dimension 6 is free of gauge anomalies coming from triangles. The same conclusion was obtained with a very different technique, more formal indeed, let me say it, by Ferruccio in a note that appeared a few weeks after ours. So with two different techniques, we arrived at the same conclusion. We're quite certain about it. Our technique is easy to extend, and it's trivial basically to extend to any higher dimensional operator that modify the gauge couplings in exactly the same way that these dimension 6 operators that I talked about today. And what is very nice is that the same techniques, the bosonic EFT techniques, can also be used to understand a bit better the relation between global anomalies or mixed global gauge anomalies in axion EFTs, and also its connection to chiral extensions of the standard model. And you can see more about that in our publication from last year that you can see here. But that is a topic for another day and for another talk. So thank you very much.
Any question from the conference room? Okay. Any question from online? I actually have a naive question. So, so can you check anomaly for all dimensional 8 operators, or is that something you want to do, or is that necessary?
Indeed, we are thinking to extend the proof to any dimension. We think that at the end you will get the same, but we haven't made the proof for higher dimensions. We think that maybe for higher dimension, it might be easier to go with a Fujikawa method to compute anomalies. Our proof already basically includes dimension 8 or higher operators, which you can obtain from these dimension 6 operators, multiplying by h dagger h, no? Because at the end, it will just give you a further power in d squared over lambda squared. So for those operators, it's basically done. But to any higher dimensional operators is something that we're working on. I cannot say that our proof, nor the one by Ferruccio in principle, already applies, but we expect the same to happen. But it's something that we're working on.
Okay.
We have a question from Mike, I think.
Oh, yeah, please. Mike?
Can you hear me?
Yes, I can hear you.
It's just more of a comment. Maybe you're already aware of it, but I think I agree with your conclusions. And I just wanted to bring your attention to a paper I wrote with Andreas Helset in 2018, where we were looking at symmetry currents and higher dimensional operator contributions to them. And then in that case, we looked at a couple of things, including one loop effects, which are all consistent with what you're saying here. But I just wanted to bring your attention to it, because I think some of the arguments in there are quite related to the arguments that you've been presenting here. But I just wasn't sure if you were aware of the paper or not, because I know it's not cited in your work.
Okay.
Just take a look.
At
maybe.
some moment, now that you mentioned, I think at some moment I saw it, but I didn't remember it could be related to this. So I will look into it. We will look into it for
sure. And on the all orders results in terms of dealing with these things with the v squared over lambda squared expansion, also quite related is the all order statements on the ward identities, which exactly are established for the background field method in the full tower of v squared over lambda squared. That's another paper with Helset as well, related, and it's the same series of works. So you just might want to take a look because it's quite related.
Sure, for sure we will do it. Thanks.
Okay, if there are no more questions, let's start to speak again.
Oh, I
Can you-
raise hand from Tyler. I don't know if the time, if not, you can ask me in Slack or by email. No problem.
If it's urgent, I think maybe he can ask now, but if not urgent, maybe we can defer that to Slack.
Okay, shall I stop sharing?
Okay, thank you. So, Jasper, right? Can you share
Yeah.
your screen?
Can you hear me first of all?
I can hear you, yes.
Perfect. Okay, let me share my screen.